So far we have discussed the fitting of linear regression models. We have used the general linear model setup. We have seen how we can fit a regression model or how we can use an analysis of variance or analysis of covariance technique to explore the given data. Depending on what kind of independent variable we have, either categorical or continuous, we choose the required general linear model. But sometimes when we talk about linear model, we do not mean the model is linear in terms of the independent variables. Rather, they are linear in terms of the parameters. In this module, we will discuss one such variation from the linear model where the model still stays linear in the parameters, but as for the independent variables, they are in a polynomial form. In the paper Regression Analysis 2, we had discussions on multiple linear regression. We had learned how and when to fit a linear multiple regression model to one dependent variable and two or more independent variables. We had outlined ways to check assumptions of linearity by looking at various diagnostic plots. In addition to that, we have seen how we can check for the other assumptions made before fitting a linear regression model to a dataset. For example, we look at the scatter plot of the residuals versus the fitted values, which checks for the inequality of variances of the error terms. We also look at a scatter plot of the residuals versus the predictor. Sometimes a plot of the residuals versus a predictor suggests that there is a non-linear relationship between the dependent and independent variables. This can be detected by looking at the scatter plot of residuals and predictor. If the plot is scattered, then it is linear, and if the plot shows some specific pattern, like a funnel-shaped distribution of the scatters or an increasing and decreasing trend in the scatter of the plot, then linearity assumption of regression is violated. Then we look further for an appropriate model. We can either think of transformation of the variables x and y, either the log or the square root or the reciprocal transformation, which are the more common ones, or we can think of a different kind of model altogether. Now, one way to try to account for such a relationship is through a polynomial regression model. The next best thing that we can do after transforming the variable is to try for a polynomial type of regression where not just the x variables, we also include polynomial or higher degree variants of the same variable which we already have. Now, suppose we have a dependent variable y and a single independent or explanatory variable. Then a polynomial regression model of order h will be given by y equals beta 0 plus beta 1x plus beta 2x square plus beta h x to the power of h plus epsilon, where h is the degree of the polynomial, y is the response vector, and epsilon is the error term. Now let us demonstrate what a polynomial regression is, or how we can fit a polynomial regression which should be fitted to the given dataset. So suppose we wish to create a polynomial that can approximate better the following dataset on the population of a certain Italian city over a period of 10 years. The data is summarized in the following table. So first, as we lay our hands on the raw data, it might be useful to chart the data so that we can observe any trend that lies between the two variables, and then we can get an idea of what the final fitted model should look like. For convenience, we modify the column year so that we create a neighborhood of 0. So let us look at the data. Given that we have two variables, one is the year, which starts from 1959 and goes all the way up to 1969, because the data set is for 10 years, and we have the population also, which is given for the corresponding 10 years that we have measured. So we first read those two variables into R, and then we put them in a data frame. We are calling it sample. So once we print sample, this is how the data set looks like. Then once we have the data set put into a data frame, as we have mentioned before, for convenience we want to modify the column called year. So we take the middlemost year, and from that we subtract all the other years. So 1959, which is the first year, from this we subtract 1964. From 1960, we subtract 1964, and so on and so forth. So in place of the column which had years, we now have values of variables which start from -5 and go all the way up to +5, with 0 being one of the data points included in my column. So we put the data on a chart. We use the plot function in R, and we plot sample year against sample population, with sample population being on the y-axis and sample year on the x-axis. Now the condition that type equals B would give me a plot where I have line as well as dot plots. So after fitting, we clearly see a non-linear relationship between the two variables. Now if we choose to fit a statistical model for prediction purpose to this data set, we would want to use something which is fitted to this particular data set and not forcibly try to fit a linear model. So as we can see, the plot shows a non-linear relationship, and at this point we can start with the search for a polynomial model that adequately approximates our data. So first we specify that we want a polynomial function of x, that is a raw polynomial, which is different from the orthogonal polynomial, which we can also fit. Now this is an important addition because the controls and the results will change in the two cases. So in case we want to fit a orthogonal polynomial, that has to be separately mentioned while fitting a model to the data. So we want a raw polynomial which is of the following functional form. Y is a function of x given by beta 0 plus beta 1x plus beta 2x square plus beta 3x cube plus beta nxn, where n is the order of the polynomial. But if I decide to fit a polynomial regression, the next question which I ask myself is what should be the degree of polynomial, or rather what should be the value of n that we have seen in the previous functional form. Now the degree of precision that we want in fitting a regression model, that will dictate what the order of the polynomial should be. Now by increasing the number of degrees of polynomial that we are using, we will increase the precision of the model. But there is also a practical problem of increasing the number of or degree of polynomial that we wish to fit. The higher the degree of polynomial, more the number of parameters that I have to estimate, more number of unknown coefficients involved in the model. So we would like to strike a balance between the degree of polynomial and the number of parameters that I want to estimate using the data set that has been given to me. If the data set is huge, then a 5th or 6th or 7th degree polynomial would not be too difficult, but we have to keep in mind that the number of parameters we want to estimate and the number of data points that we have in our data set, that has to have a parity. More number of data sets will allow us to fit more number of parameters or a higher degree of polynomial. However, if the data set is small, we will have to restrict ourselves to a 2nd or a 3rd degree polynomial, as we will see in the example in the next few slides. Now, in order to fit a polynomial regression, suppose we seek the values of beta coefficients for a polynomial of 2nd or a 3rd degree for the data set that we have regarding the population of the Italian city, which has been collected over a period of 10 years. So the R code for fitting this regression model is given here on the next slide. It says the first fit is done using the LM function, where we regress the sample population on a polynomial of degree 2 on sample year. Now as you can see, here also we are using the LM function. As I had mentioned in a previous module, whenever we fit a regression model with x variables which have functional forms other than the linear form, we can still use the linear model function in R. The reason being, the LM function works for a linear model which is linear in the parameters. If you notice the 2nd degree polynomial that we are trying to fit here, we are taking higher order polynomial form of the x and not the coefficients. So the coefficients are still linear, so we are still free to use the LM function in R to fit the polynomial regression model. So we call for a 2nd order polynomial regression model, and R gives me the output, which is the coefficient estimate for the intercept, the coefficient estimate for the 1st order polynomial, and coefficient estimate for the 2nd order polynomial, which is corresponding to x square. And the regression coefficient estimates have the same interpretation as before, in the sense that if you look at the output, the intercept has an estimate of 5263.16. So in the absence of all the covariates or the explanatory variables x, this is the mean value of y. Now for the first coefficient x, we have the estimate as 29.32, which means if we change x by 1 unit, then y changes by a unit, 29.32. Similarly, if the second coefficient, which is corresponding to x square, if that changes by 1 unit, then the polynomial, from the polynomial regression, y will change by 10.59. Because 10.59 has a negative sign attached to it, we know that in case the second coefficient corresponding to x square increases by 1 unit, then y would decrease by 10.59 units. On the next slide, we have fitted a similar polynomial, but now we have increased the degree to 3. The coefficient outputs in R for fitting a polynomial of degree 3 is the same as before, as well as the interpretation also remains the same. Now we have seen the use of the poly function in the LM in order to fit the regression model. So we have used LM, and then we have written sample population, which is our response, regressed on poly, and within brackets we have the name of our x variable, comma, the degree of polynomial, which is 2. Now in case we choose not to use the polynomial function, we can still fit a polynomial of second degree in R using the following functions. So here we are fitting a regression model of first order, where I am simply fitting a linear model using the LM function of sample population on sample here, and the output is simple enough. We have one estimate for the intercept, another estimate for the slope corresponding to the sample year variable. On the next slide, we have the same model fitted but with a higher degree of polynomial, but here instead of using the poly function, we have used the LM, where we regress sample population on sample year plus I of sample year, which has been raised to the power of 2. This is an alternative way of mentioning that the model that we wish to fit is a polynomial of degree 2. But you will see that from the coefficient estimates, it's clear that either we use the polynomial function or we can use the given LM function with the I, but it will give us the same estimates for the coefficients, and this is what we are more interested in. The same thing can be seen for the third degree polynomial as well. So you will see that the two sets of different codes return the same estimates of parameters for fit 2, fit 2b, as well as fit 3 and fit 3b. So the function poly is useful if you want to get a polynomial of high degree, because in the previous slide you have seen that specifically mentioning separately what degree of polynomial you want would require you to write it out every time when you're fitting a model. However, if you're fitting a polynomial of higher degree, instead of separately writing each covariate, we would rather use the poly function and simply mention the name of the independent variable, and after the comma put the degree of which polynomial we wish to fit to the data set. So the function poly is useful if you want to get a polynomial of high degree, because it avoids explicitly writing the formula. If we specify raw equals true, this is one of the arguments required in R. The two methods provide the same output, but if we do not specify raw equals true, the function poly gives the values of the beta parameters of an orthogonal polynomial. As I've mentioned before, there are two ways of fitting it. In case we specifically want the raw polynomial fit, then we need to mention that raw equals true. Now the output of summary fit 2b is the same. We obtain the values of beta 0, beta 1 and beta 2, which appear to be significant in all the cases. Now if we look at the equation of polynomial of degree 2 of our model, it will be given by the following functional form. And if we want to fit a polynomial of degree 3 using the estimates of the coefficient, we will see that they are of the following functional form. So now out of the two regression equations shown above, in the second equation beta 1 and beta 3 are not significant, then the best model is the polynomial of second degree. Also, if we look at the R square, In the second degree model, it is 94.07, which is greater than the R square value that we get from the fit of polynomial of degree 3. So it seems that there has been an increase in the accuracy of the model, but is it a significant increase? We can compare the two models with an ANOVA table, which we will demonstrate in the next slide. Now before we move on to that, let me explain the concept of multiple R square, where when you're fitting a regression model with multiple covariates, they could be a polynomial regression or they could be independent X variables. As you increase the number of covariates, the multiple R square will get better and better. But at what cost? In case we increase the number of covariates, I'm also increasing the number of parameters that I have to estimate when I'm fitting a regression model. So at one point in time, we have to stop and think whether we want to include more variables and increase the complexity of the estimation process, or we want to strike a balance between the number of degrees of polynomial and the precision of the model for estimating the required parameters. So in this case, we see that although for a polynomial of degree 3 there is a slight increase in the R square value, but still the beta 3 coefficient, which corresponds to the third degree polynomial, is not significant, which tells us to use a polynomial of degree 2 instead. In order to explicitly test whether one model has been significantly better than the other, we can use the ANOVA table. So fit 2 and fit 3 have been the two polynomial models, and using the ANOVA function we get the following output in R, which can be used to test the significance of one model over the other. So we are given the RSS values. We have the value of the F test statistic, which is used to test the significance of fit 2 over fit 3. As we can see, the statistics given to us here is 3.98. that is the value of the F test statistic. We are given the RSS values, and corresponding to the F test statistic, we have seen the p value is 0.08. Now taking a significance level of 0.05, we can see that the null hypothesis is rejected, and we can see that the ANOVA test that was performed to test whether fit 2 was better than fit 3 as an alternative hypothesis has been accepted. So since the p-value is greater than 0.05, we accept the alternative hypothesis that there wasn't a significant improvement in the model. Now our concern now is to represent our output from R graphically. We want to now graphically look at the plots, or look at the line, fitted line, once we fit a polynomial of second degree. Now in fact in R there does not exist a function for plotting polynomials, so we must therefore proceed with graphic artifacts which are still available to us, and the workings could be slightly laborious, but we will still give it a try in order to visualize the fitting of the second degree polynomial model. So using the next few lines of code, in R we can fit a polynomial regression model to the data set, and what we get as output is shown on the next slide. So we can see that instead of the straight line, the two polynomial regressions that we have fitted are a better approximation of the actual trend of the data that we have. So if we would instead obtain the graphs of continuous functions obtained instead of using the previous codes on the previous slide, we could also proceed in the following manner. We first create the polynomial equation we previously found, and at this point we plot the coordinates of sample 1 and then the created curve with the curve function, and the output that we get is attached at the end of the slide. So in this module we have learnt that although some models are linear in the parameters, they need not necessarily be linear in terms of the independent variables. For example, the models that we have fitted here using R, they have polynomial of order 2 on order 3. So we have seen how explicitly we can fit such a model which is still linear in parameters. However, we call it a polynomial regression because it's polynomial in terms of the independent variables which are involved.